Hey there, Zach Stone here from electricalpereview.com, and you're about to watch a video on how to solve any single auto transformer problem on the Power PE exam. Interested in learning more about our online class? Come check us out at www.electricalpereview.com. We'll see you soon.
So the first thing is we're going to start off with ideal single-phase auto transformers. I find people are often intimidated by auto transformers the first time they use it. They're real easy. I'm going to show you how we can pretty much figure out any relationship we need to using the circuit analysis we're already familiar with. So we don't need to learn anything new. As long as we're comfortable with KVL and KCL and transformers in general, we can figure this out easily. So really quick, the reference handbook, your auto transformers are located on page 62. However, the reference handbook only shows you the diagram and the formulas for what kind of auto transformer. Who's got their handbook open? I believe it's this one over here on the left, right? They don't give you both circuits. They're very similar, but there's one big difference. Everyone's saying the one on the left? Yep. All right, question number one up here. How do we know the difference between a step up or a step down auto transformer based on the circuit? So over here on the left, is this step up or step down? And more importantly, how do we know? How do we know? Everyone's saying step up. Yep, I agree. We can call this a step up auto transformer, commonly referred to as what? Commonly referred to as what? Starts with a B, boost. You got it. We're boosting that voltage up. It's a boost auto transformer. We're boosting that voltage up. How do we know? Your classic transformer ratio formula is A equals N1 over N2 equals V1 over V2 equals I2 over I1. In other words, if I've got more number of turns on the primary, I'm going to have more what on the primary? I'm going to have more voltage, right? Your number of turns correspond to the voltage. Visually, we can look at it like this. Do I have more turns on the primary or the secondary of this auto transformer? Who can tell me? Give me the variable in the chat. What's the number of turns using the variable on the primary side? Here's our primary. So from here to here, how many number of turns do we have? We have just NC, which is this is the common winding. So this is N common. In other words, N1 to N2 for the auto transformer on the left, N1 is going to be equal to what? Here's my primary. So the primary turns from here to here is the primary number of turns from here to here. That's just N sub C. Okay. Now let's look at the secondary side. Here's my secondary. Who can tell me in the chat using the variables on the screen, how many number of turns are on my secondary? I don't just have NC, but now I also have what in series with NC? I have NSE. This is called the series winding. So the number of turns in just the series winding from here to here, plus, right? Got to get down here, plus the number of turns through our common winding, right? So N2 for this auto transformer, it's not just N sub C or the number of turns in our common winding, it's NSE plus NC. All right, looking at this, are there more number of turns on the primary side or are there more number of turns on the secondary side? Secondary, right? The same number on the primary is on the secondary, and then we're adding more turns. So if I have more turns on the secondary side, am I going to have more voltage or less voltage on the secondary side? I'm going to have more voltage, right? That means this is a voltage step up transformer. More number of turns on the secondary means the secondary voltage is bigger than the primary voltage. Does that make sense? Now, if we're stepping up, what is the current doing? If the voltage is stepping up, the current must be stepping down. Good job, everybody. If you're not familiar with this, when it comes to transformers, if your voltage goes up on the secondary, your current goes down. And if your voltage goes down, your current goes up. They're always going to be opposite, right? They're always going to be opposite. So if our secondary current is bigger, I can say, if our secondary current is smaller, secondary current is smaller, IH is less than IL. the current on the high voltage side is going to be less than the current on the low voltage side. Does that make sense? Now, the reference handbook is nice enough to give us this diagram here on the left for a step-up autotransformer. And I believe they do show the direction of the common current, don't they? Can anyone confirm that has their reference handbook open? They do? Great. How do we know that the common current is going down away from this node? How do we know the direction? KCL, good job. Who said that? Adam, fantastic. Yep. If I were to write a KCL equation right at the common node here, and I know that my current on the high side is smaller than the current on my low side, right? Voltage goes up from left to right, so current goes down. What's the only way that the secondary current, IH, can be smaller than my primary current, IL? Does that mean we have current flowing into this node, adding to IL? Or the current has to be flowing away? Yeah, we're subtracting the common current. In other words, here's our KC equation for IH. Ready? Current entering equals current leaving. If IH is leaving, IL is entering, and now we subtract IC. Does that make sense? The only way that IH can be smaller than IL, because it's a step-up transformer, voltage goes up, current goes down, is we're subtracting our common current. The current has to be leaving that node, flowing away from that load. IL flows in, some of it flows out, and the rest of it continues on to be IH, secondary current. All right, let's do the same exercise for the diagram on the right. So they don't give us the diagram on the right. Who can tell me, is this a step up or step down autotransformer? Look at the number of turns, right? If I've got N1 to N2, this is going to be the series number of turns. This is the common number of turns. Who can tell me what's N1 for this autotransformer on the right? What is N1 this time? Jonas said N1 is the sum of the series turns and the common turns. Great. And of course, what is N2 this time? What's our secondary number of turns from here to here? Just NC. You got it. Do I have more number of turns on the primary or the secondary this time? I have more number of turns on the primary, right? That means we're stepping down. When I go from left to right, from primary to secondary, I'm going from more number of turns to less number of turns, which means this time this is a voltage step down auto transformer. So remember, they don't give us this diagram in the reference handbook, but we can use all the same relationships to figure it out. All right, step down auto transformer, also known as a what? If step up is boost, step down is buck. You got it. We are bucking the voltage back. Bucking the voltage back. All right, on the primary, is this going to be VH or VL? If I've got more number of turns on the primary, that means I've got more voltage on the primary, right? So this is VH. Same thing over here. Is this going to be VH or VL? We can use process of elimination, or we can say, well, I've got less number of turns on the secondary, right? Primary has not just NC like the secondary, but it also has NSE being added to it. Less number of turns means less voltage. So this is VL for the low voltage side. You can still call this V1 and V2. Same thing, V1 over V2 for primary and secondary. The handbook, the reference that they borrow that diagram though specifies VH and VL. Same thing as V1 and V2 as long as you label it properly. All right, question. If I'm stepping down from left to right, what is my current doing from left to right? Stepping up or down? Voltage goes down. This time, current goes up. You got it. Current stepping up. So on the secondary side, careful. This is the current on the low voltage side. And on our primary, entering the common node, this is the current on the high voltage side. How do I know what direction my common current flows in? Can I write a KCL? Right at this node, just like before, Kirchhoff's current law. Is IL, the current on my low voltage side, bigger or smaller than IH, the current on my high voltage side? Current goes up, so IL this time is bigger. How do I make IL bigger, right? So we've got current entering this node, and IL leaves this node. So IL has to be IH plus something else. It's got to be plus because IL is bigger than IH, not HH. IL is bigger than IH, so we've got to add the common current this time, right? This time the current is flowing up through our common winding. See how easy that is? Does that make sense? IL, the current on the low voltage side, or we can say IL, the secondary current, is bigger because the voltage is stepping down, so the current's stepping up. So if the current's stepping up, IL is bigger than IH. The only way IL can be bigger than IH is if we add the common current this time instead of subtract. Does that make sense? Pretty easy, right? You ready for an even easier way to know? Over here on the left, did we say this is a step up or step down autotransformer? Tell me in the chat. Is this step up or step down? Voltage step up. So that means the current is doing what? Current is going down. Guess what? Here's your trick. Current is going down. If the current goes down, your common current goes down. Over here on the right, is this voltage step up or step down? Over here on the right, we know our voltage is stepping down, so our current is going up. So is our common current. Neat, huh? That's just a coincidence, but it's an easier way to remember it. Light bulb, says Tyler. Cool trick, says Cyan. Yeah, easy. It's the little things you figure out after doing hundreds and hundreds of practice problems that really increase how fast you can solve these problems. All right, let's look at the reference handbook formulas. So the first one we're going to look at is on the left. And all of this, of course, is located on page 62 for Autotransformers in your reference handbook. Who can tell me, what is SIO? What does SIO stand for? SIO. Input output, says Connie. Yep. SIO. First of all, what is capital S? What kind of power? This is apparent power. Input for I. And output for O. Output. This is your input, output, apparent power. Okay. We're dealing with, is this an ideal or non-ideal transformer? We're dealing with what? Ideal transformer. What does it mean for a transformer to be ideal when it comes to input and output power? No power losses. Input equals output. Who said that? It's going fast in the chat. I missed it. David Chuk said input power in equals power out. Beautiful. Yep. So let's draw it. Apparent power. Make sure you use your magnitude brackets, right? Not complex, just apparent power. Apparent power in equals apparent power out. In other words, solving for SIO is the same as solving for a power in or solving for a power out. How do I calculate the apparent power for a single phase transformer? It's the product of what two variables? Product of what two variables to calculate power? Who can tell me? V and I. Yep. So to calculate power, we need the product of voltage and current. If this is our input power, which V is this and which I is this? And for now, don't worry about H and L. Give me 1 and 2 first, and then we'll use H's and L's. Yeah, this is going to be V1 times I1, right? The voltage on the primary times the current on the primary gives me my input power. Likewise, how do I calculate my output power? This is the single phase apparent power formula, right? Single phase apparent power formula is the product multiplication between the magnitude of the voltage and current. How do I calculate the output? This time it's V2 times I2. Now let's rewrite this using the autotransformer. Let's see, the step up on the left. What is V1 and I1? The step up on the left. What is V1 and I1? What is the voltage and current on the primary? That's the voltage on the low voltage side and the current on the low voltage side, right? Let's use red. So that's the same as VL and IL. All right, what about the output power of a step-up autotransformer? What's the V and I on the secondary? Now it's the voltage and the current on the high voltage side. So it's VH, IH. So we just calculated SIO using either the primary side values or the secondary side values. And they're going to be equal to each other. Why? Who can tell me? Why will these be equal to each other? Looking for a vocabulary word in the chat. Ideal. Who got that first? Good job, Andrew. Excellent. All right, if that's SIO, what the heck is SW? We know what NSC and NC is, right? This is the number of turns on the series winding, number of turns on the common winding. What is SW? Winding, right? This is the winding power. So SW is the winding power. Now, here's the most important thing to remember about autotransformers. Who knows in the chat? What's the relationship between the power in the common coil here and the power in the series coil here? Or over here, what's the relationship between the power in the common coil here and the power in the series coil here? They were equal. Excellent job, everybody. Yeah, that's typically the last thing to learn when it comes to autotransformers. So SW is the winding power. This is the same as the common winding power or the series winding power. They're the same. In other words, I can say magnitude S on the left equals magnitude S on the right. And I'm going to use the subscripts C for common. The apparent power in the series winding is equal to the apparent power in the series winding. Make sense? All right, just like before, we looked at how to calculate the apparent power in and the apparent power out. I want to see how to calculate the apparent power using the common winding values and the apparent power using the series winding values. Ready? All right, just like before, who can tell me apparent power is the product of what two variables? Specifically, single phase apparent power is the product of the magnitude of what two variables? V and I. Good job, Derek. All right, if I want to calculate the apparent power in the common winding for this step-up autotransformer, that means I need the voltage across the common winding and the current through the common winding. What's the voltage across the common winding from here to here? It's going to be V what? VL. Good job, Nikki. You were first. All right. What's the current through the common winding? I common. You got it. All right. That's going to be equal to the voltage across the series winding times the current through the series winding. Do we know the voltage across the series winding from here to here? Not yet. Can we calculate it using KVL? Sure can. If I know the voltage from here to here, this is VH from plus minus, and from here to here is VL. What's the voltage from just here to here across our series winding? Can I say that the voltage across the series winding is going to be magnitude VH minus magnitude VL? See that? That's just a Kirchhoff's voltage law, KVL. In other words, the voltage across NSE, the voltage from here to here, is going to be the voltage from here all the way down to the bottom minus the voltage at the common node down to the bottom. Will give us just the voltage from here to here. All right, there's our voltage. Now we got to multiply by the current. What's the current flowing through NSE, the series winding? That's going to be what? It's going to be the current on the high voltage side, right? It's going to be IH. Careful, not IC this time. It's going to be IH. Ta-da. So these two relationships are equal. The power in the series winding is equal to the power in the, I got that backwards, excuse me. The power in the common winding, rather, is equal to the power in the series winding. Now, going back to this formula before we move on, you'll notice that, so here's SIO on top, here's SW on bottom. So all this formula tells us is that the ratio of the input or the output power to the apparent power in either of the windings is equal to the ratio of NSE plus NC divided by NSE. That's all. All right, over here on the right, we've got a couple more auto transformers in the reference handbook. They look a little different compared to what we're used to, right? Maybe we recognize them a little bit and we're used to the single phase transformer A ratio formula we're used to. Let's see if we can derive these two to make more sense out of them, right? They're a little unfamiliar, so let's go ahead and make them more familiar. So I'm going to start with this same transformer A ratio formula down here. And all that is A, right? My transformer ratio equals, I've got N over N, and I'm going to fill in the subscripts here in a second, equals V over V equals I over I. I'm going to use ones and twos for primary and secondary, and then we'll get to L's and H's. So my A ratio, whether it's step up or step down, is always going to be the number of turns on the primary winding to the number of turns on the secondary winding, right? My transformer ratio is also going to equal the ratio of the voltage on the primary side to the voltage on the secondary side. All right, here's the trick. The subscripts for my N's and my V's are going to be on the same side of the fraction. Is that true for my current? We said before, turns corresponds to voltage, right? If I've got more number of turns on one side, that means I've got more voltage on that same side. But if my voltage goes up, my current has to go down. It's a transformer. So I've got my ratio is equal to turn on primary to turns on secondary, voltage on primary to voltage on secondary. And here's the trick. These subscripts flip-flop, they change. It's equal to the current on the secondary side to the current on the primary side. Ones for turns and voltage, twos for turns and voltage. And now the primary and secondary change places when we deal with current. Again, why is that? Well, when the voltage goes up, the current goes down. When the voltage goes down, the current goes up. Let's fill in these subscripts for a step-up auto transformer first. Let's say step-up auto transformer. Essentially what we're doing is we're deriving a cheat sheet that'll let you solve any auto transformer problem on the PE exam. And you've got some good homework for this class on auto transformers as well. All right, let's see if we can derive these relationships up here for step up. So looking at the diagram on the left on your workbook notes, A is going to equal, what is N1? What's the number of turns on the primary for a step-up auto transformer? N1 is equal to what? The number of turns on the common winding. You got it, NC, great. N1 over N2. What's N2? What's the number of turns on the secondary side for an auto transformer? This time it's the sum, right? NSE plus NC. The number of turns in our series winding plus number of turns on our common winding. Great. Next step, let's look at the voltages. I've got V1 over V2. What's a V1 for a step-up auto transformer? What's my voltage on the primary side? VL, good job, Johnny and Jonas. All right, what's my secondary voltage? V2 for a step-up auto transformer. It's what? VH. Good job, Maggie. All right, now let's do the current. Remember, what's the trick with the current? These subscripts flip-flop. Now I've got the secondary current on top and the primary current on bottom. What's the secondary current for my step-up auto transformer? Secondary current is now the current on the high voltage side. So we've got IH. And what's my primary current on my step-up? Primary current is IL, or the current on the low voltage side. See where these come from? So the reference handbook gives you the formula for the step-up, the boost, VL over VH. VL over VH equals NC over the sum of NSE and NC equals the sum of the turns in the common winding, or equals the number of turns in the common winding to the sum of the common winding turns on the series winding turns. Same thing, IL over IH, they flip-flopped them. So IL equals the sum, IH equals NC, right? IL equals the sum, IH equals NC. Ethan said, great explanation on this. Fantastic, Ethan. Glad you're enjoying. We're going to do one more exercise on this page. We're going to do the same thing, more importantly, for the step down, right? Remember, they don't give you the step down auto transformer relationships. Can we derive it on our own quickly without wasting time? You betcha. So here's our basic single phase transformer formula. What is N1 for a step down? So we're using the diagram on the left. What's N1 this time for a step down? Is it NC like last time? It's the sum, right? It's the sum. If I'm looking at N1 for a step down, I start here. Here's NSE, the series winding turns. Here's NC, the common winding turns. So from here to here is the same as this number of turns plus this number of turns. So N1 is going to be the sum, right? Notice we've traded places compared to before. All right, what's N2 for our step down? Here's our secondary, right? For 2. So I'm just looking at the number of turns from the common node down to the reference node. So now it's just NC. Make sense? Starting to click. All right, what is V1 for my step down? Is it VL like last time for my step up? That 1 means primary. Now it's VH. What's V2 for my step down? It's VL. What's I2 over I1? I2 is going to be IL, right? And I1 is going to be IH. So I've got IL over IH. See how easy it is to derive the relationships using the regular, boring, single phase transformer ratio. Make sense? A couple of key things I want to point out before I move on. Who can tell me in the chat, what's the most important thing to remember about the single phase transformer ratio formula that I just circled? What's the most important thing? How do we remember it intuitively? A equals the ratio of N's equals the ratio of voltages equals the ratio of currents. What's the one thing to remember? N1 equals, or, ooh, careful, Yusuf. I think you got N1 over N1. Current is flipped. Great job, Ellie and Sand. Yeah, the current subscripts are flipped. Voltage goes up, current goes down. Voltage goes down, current goes up. So my current subscripts are going to be in the opposite placement compared to my voltage subscripts. We know our voltage subscripts are going to match our turn subscripts, right? A is equal to the ratio of N1 over N2, equal to the ratio of V1 over V2. Here's the trick. We're going to flip-flop, equal to the ratio of I2 over I1. And last but not least, how do we remember, what's the really quick cheating shortcut way to remember the direction of our common current? What's the cheat way? Not KCL. What's the cheat way? How do we remember the direction of the common current? Up is up. Yeah. Good job, Stan. Yep. If the current steps up, common current goes up. If the current steps down, common current goes down. Ta-da. All right. Any questions before we do an example for a three-phase ideal transformer on the next page? Mark said, is this true for non-ideal? Nope. These are ideal transformer relationships only, but we will be exploring non-ideal probably tomorrow night. Jeffrey said apparent power, same for step down. Yep. Good question. So step down apparent power would be either VH times IH, right? Primary voltage times primary current, or it would be secondary current times secondary voltage, right? Good question. Joshua said, why does S series equals S common? Good question, Joshua. That's how autotransformers function. Long derivation that we don't have time for, unfortunately, tonight. But the same amount of power will exist in both. And here's a good question. Notice that your voltage polarities and your current direction are opposite compared to the voltage across the coil and the current flowing through the coil. When do we consider IC in a calculation? Asks, is it Namrata? Or I guess Nam for short, parentheses. Good question. Namrata, if you know IL and IH, can you calculate IC? The problem says calculate the common current in a step-up autotransformer if IL equals blank and IH equals blank. Sure can, right? All right, good questions. So let's do an actual hands-on example for a three-phase ideal transformer. Let's go ahead and flip to page 16.
Hey, that's it for this short video. We hope you enjoyed. If you'd like to learn more, or if you're interested in joining our live class for the Power PE exam, please visit us at www.electricalpereview.com. We'll see you soon.